So we're now ready to talk about the second major topic in the course, which is the C++ standard template library. So the first part of the course, which we've gone through now, focused largely on an overview of C++ abstractions over the years, focusing on data abstraction, generic programming, and object-oriented programming. And now that we've kind of covered those concepts, and we've actually talked about some pretty advanced features along the way, we're going to focus our attention on the second major topic, which is the C++ template library. And this should take us through the next couple of weeks because there's a lot of material to cover here. This material, as always, is split between some slides to give you a conceptual understanding of what we're going to cover, and then lots and lots and lots of code examples in order to make it all come together. And as usual, you can get all the code at my repository, and the slides will tell you where to go. Speaking about slides, I'll put out the video lectures from yesterday's course shortly, and you can go up and take a look at those as well. The video lectures are actually up already on my YouTube playlist. I haven't put the slides yet, but I'll do that shortly. Okay, so here's kind of an overview of what we're going to cover over the next week or two. First, we're going to talk about what is the standard template library, and then we're going to talk about why on earth would you want to use it, and of course, the answer there is generic programming. And then we're going to talk a lot about STL concepts and features. So we'll talk about helper classes and function templates and containers, iterators, generic algorithms, function objects, also called functors, adapters, all kinds of things. And then we'll look at several comprehensive examples of STL. We'll also look at tons and tons of examples as we go through the bits and pieces of STL. Okay, so what is the C++ standard template library? Well, as you can see from the diagram here, which we've looked at before, but this will give us a chance to revisit this. STL is a subset of the overall standard C++ library that provides a set of well-structured generic C++ components that are designed to work together in a more or less seamless way. And I qualify it with more or less because there's certain combinations that are intentionally not designed to work together, and that's okay. That's by design, and but there's lots of other stuff that does work together. So you can see here that STL is what I'm putting in the little red egg-looking shape, the oval, and it's part of course, the much larger C++ standard library, but I would have to say it's probably the most important single part of the C++ standard library. And you can find lots more information about STL if you take a look at the link at the bottom of the page. So what are the actual components or elements in STL? Well, there's about a half dozen or so different components, some of which are really important and others of which are kind of ancillary to help support the really important ones. So the stuff that's not so important are things like helper classes, like class pair, we've talked about this briefly, various operators to do encapsulation and decoration of relational operations and IO streams and all kinds of stuff. But then when we get into the more interesting parts, we get into containers, iterators, generic algorithms, functors, and adapters. Those are the real money elements that we have in STL. So now let's talk about the actual parts of STL that matter. So the first part that matters are containers, which are holders of data elements, and they typically hold them by value. Then there's also algorithms that act on the elements in containers, and there are lots and lots of algorithms. They're iterators that serve as the bridge between containers and algorithms. And iterators essentially take the different parts of a container, starting from perhaps its beginning and going to its end, and then provide that as a means to allow the algorithms to access that range of data within the containers. And this is all very carefully designed to be maximally flexible. So if you end up with iterators that don't necessarily point to the beginning of a container or the end of the container, you can still do algorithms on subsets of the overall data as long as you have valid iterators. And then there's something called functors, and functors essentially are used to guide the behavior of either algorithms and or containers. And we'll see there's a bunch of different ways to apply them. And finally, then we have adapters, which can be used to convert the other types into things that work with each other. For example, there's things called container adapters that allow existing containers that we'll talk about shortly, like vector and dec and list, to be adapted to look like other abstract data types that you're no doubt familiar with, like queues and stacks. There's also so-called iterator adapters that take containers and make them work in contexts where algorithms expect iterators. And then there's also a whole pile of things called function adapters that can be used to take various functors and adapt them to go from unary or binary expectations of binary operations to unary operations, or be able to take the result of one functor and convert them to another. So those are all the core concepts in STL, core components in STL. And we're going to talk about each of them in great detail. So by the time you're done with this class, you will have been exposed to all the relevant elements in C++ STL. And you'll also get a chance to see a lot of the really advanced features in C++ demonstrated in the context of STL. A lot of the work that's gone over the past decade or so in C++ is figuring out ways to enhance the language in order to better support and better optimize the C++ STL containers and iterators and algorithms and so on. So you'll see a lot of real synergy between the concepts we've talked about so far and how they're realized and demonstrated in the context of STL. So, of course, STL is really about generic programming. That's its claim to fame. It's probably the first widespread example of a generic programming-based library. And that raises the question, what is generic programming? So you can take a look at the link at the bottom of this slide to give one perspective on this, and I'm going to summarize it here. But going and reading the link is very helpful, especially after you know enough to be able to interpret the meaning of what it says, because of course it's written in a fairly technical way. So generic programming is a programming paradigm in which algorithms are written in terms of generic types, which can then be instantiated as needed from specific types or for specific types that are provided as parameters to the algorithms. So here's a very simple example. You can see here's the C++ STL find algorithm. And without getting too wrapped up into the nuances of what it does, because we're going to talk a lot more about find later, you can see that find is a generic function that takes two parameters, two type parameters, one of which is called an input iterator, and the other of which is called type name t. So I think we know what t is. T is typically the type of the element we're working on. And what we do then in this case is we go ahead and define the signature, the method declaration for find, to take two input iterator parameters. One is going to be pointing to the first element in the range we're going to search for to find the element. The other is one past the end, or the last element in that range. And then we also take a const tref, where t is the parameter, and of course const ref means pass it by value. So that's the signature. You can also see that find returns an input iterator. The actual implementation of find is very simple. What it does is it goes from beginning to the end, not including the end, but from the beginning to the end, while first not equal to last. And every step along the way, it checks to see whether the dereferenced iterator first is not equal to the value. So obviously when it is equal to the value, this loop will stop, and then we'll return wherever we happen to be pointing to at that point. If it doesn't get a match, then it increments the first iterator by 1. So this looks like pointer arithmetic, and in fact, you'll see that in some contexts it is. But it can also be using the overloaded operators defined on iterators, much in the same way that our atomic op example we just looked at allowed us to override the plus and minus operations. So that's basically the find algorithm. You can see it's intentionally designed to be a generic type. It's meant to be reused by many different concrete types or specific types. Down here at the bottom, I make a very simple test case for this. I define myself something called a vector, which is a very common C++ so-called sequential container. And I give the values of the vector 1 through 4. Doesn't really matter what I give them, really. And then I go down and I call the find algorithm, and I pass in the beginning iterator to the vector. So begin is a factory method that returns an iterator that points to the beginning of the vector. That's v.begin. And then v.end is the end iterator, which is one past the last item. We'll talk more about what it means to be one past the last item in a moment. And then I pass in the value 3. So what this is going to do is it's going to go searching from beginning to end in that range, trying to find something that matches the value 3. And if we get a match, we're going to get back an iterator, which I named I here, using the auto type deduction keyword that's part of C++. So this is actually returning an iterator to an element. And if the iterator is to an element that corresponds to actually finding the value we were searching for, which in this case is 3, then in that case, I will have a value that's not equal to v.end. So that would be an indication that we actually found the element we're looking for. Conversely, if we try to find, like, I don't know, element 8, which is not in the vector, then we would get back an iterator that is equal to v.end. And if you look at the code up there, you can see how that works. It'll keep looping until it reaches the end, and if we haven't found it, we'll return the last iterator, or the one to the end of the range. So you can see that this is an example of writing a generic piece of code that can be configured and customized for particular types, in this case a vector. Likewise, one of the other cool things about STL is we can keep the same piece of code. We can keep the same find algorithm we have up there, except now we can replace the data type that it works on. So in this case, we're going to replace the use of a STL vector container, which I show here, instead with a native array of integers. And by the way, I could have made this an array of doubles too. I just wanted to keep it pretty common to the example from before. So we have an array of integers, which also happen to have the values 1, 2, 3, 4, but they could be different. And then we go ahead and we compute the last or the end of that iterator range by saying A, which is the array, plus size of A divided by size of star A. And that's just a common trick to find out how many bytes of content are there in the array A. And then what we can do is then we can go ahead and say, try to find the value 3 in the range A to E, where E is 1 past the end of the values in the array. And just like this code worked fine using iterators that are explicitly returned from the factory methods on vector, v.begin, v.end, so too will this find operation work just fine on integer pointers that are passed to the find operation. And that's because STL is cleverly written, so its generic algorithms will work either for built-in types, where ++ and star are pointer operations, as well as user-defined or library-defined types like vector or dec or list and so on. And this is cool because as long as you have an iterator that has the necessary operations defined on it, this generic code will work nicely and will work transparently. So we'll see a lot more of examples of this as we go through the slides, but I just wanted to give you the kind of the Cliff Notes summary first so you can kind of see where we're headed with this. So that's what generic programming is. And one of the things that makes generic programming so powerful is that you can add new algorithms and reuse existing containers. You could add new containers and reuse existing algorithms. You can have new containers and new algorithms that work with the existing set of iterators. And this gives you a tremendous amount of reuse. It gives you a tremendous amount of extensibility because you can leverage what's already there and not have to start over from scratch. And when I think about this, kind of metaphorically, I think about like the Transformers toys and the Transformer TV show and movies and so on, where the trucks and the cars and so on, the vehicles can turn into the robots and they can morph themselves, if you will, from one shape to another. And it's kind of what STL is about. It's about moving around and extending and being flexible enough to be used in new contexts in new ways without having to write any new code or very little new code. Okay, so that's a quick overview of STL. Now let's start talking about why would you want to use STL? What's the benefit of this? And we're going to go through a couple of different motivations, starting with reuse, which really means write less code, do more by leveraging what's already there. And this is such an important concept. If I could teach a course on just reuse, I would love to be able to do that. We don't really have a course like that, so I sneak the topics into my other courses I talk about. But thinking about software reuse and writing multi-use componentry and multi-use classes and functions is very important. And that, of course, is exactly what STL is about. It's a ton of reusable algorithms, reusable containers, reusable iterators and functors and adapters and all this good stuff. So how do we get this reuse? Well, one way we get it is that the STL, the standard template library, elements, especially the containers and the algorithms for that matter, hide many low-level, complex, tedious, and error-prone details. So you don't have to worry about this plumbing. You don't have to wrestle with these low-level details. You can focus on the problem you're trying to solve, which we sometimes call the business application or the business logic. I don't know why we call it that, but that's the word business logic means sort of meeting the customer needs or meeting the requirements. So some of the things that STL will do for you that you no longer have to worry about is it'll manage dynamic memory management, allocating and deleting pointers and arrays of pointers and arrays and so on. It has, of course, very complicated data structures and algorithms. It has things like hash tables and red-black trees and all kinds of other good stuff that you really don't want to have to write. And then it also has all kinds of support for very sophisticated optimizations based on concepts like partial template specialization and explicit template specialization and so on, which we'll talk about in due time. So basically all the inner workings that provide all these complex reusable elements are shielded from you by the nice STL wrappers, and facade, I guess, is a good term for that. So STL provides a facade, which is a simpler to use, very composable and uniform means of accessing some really powerful data structures and algorithms. One thing it also does is it helps to ensure type-safe plug compatibility between STL components. And the way this works under the hood is that STL is based on static type checking, which means that it's doing the checking at compile time and link time. And so by the time your program goes to run, there shouldn't be type errors in your code unless you've done some crazy things. So let's pretend like you haven't done crazy things. So in that case, STL will do static type checking. So your program is more likely to work correctly as long as you play by the rules, and it'll detect violations of things that don't play by the rules automatically at compile time or link time. And it also, because of this, because of the fact it uses stronger type checking, it can afford to do all kinds of very sophisticated optimizations. And this is what Bjorn Strustrup refers to as zero overhead abstraction, or the zero overhead principle, if you go watch his little video about that, which is very insightful. And so the strong type checking allows a lot of these things to be detected at compile and link time, and also optimized at compile and link time. So here's just a very simple example. We're going to define ourselves two objects of two different containers. We have a vector of ints and a list of ints. And then we're going to go and try to apply the sort algorithm, the generic sort algorithm, on both of these containers. Well, it turns out that you can sort a vector of ints no problem, because the sort algorithm expects something called a random access iterator, and a vector supports a random access iterator. So that works just fine. However, a list does not support a random access iterator. Instead, it supports something we'll talk about called a bidirectional iterator, which is not as powerful as a random access iterator. So when you try to sort a list using the same syntax that you use successfully for sorting a vector, the code isn't going to compile. And that's, of course, by design, because they're not meant to be plug compatible. So this is a good example of type-safe checking to ensure we don't have incompatible code that doesn't actually work correctly or doesn't actually work efficiently. Another thing you get with STL is tremendous flexibility. So you can take it and adapt it and bend it and mold it in all kinds of interesting ways to make it do your bidding, like a contortionist. So let's take a look at a couple of examples. One example with respect to flexibility is that iterators decouple algorithms from containers. And so here's a cool example, very much like what we looked at just a minute ago with the find algorithm, where instead of differentiating between a vector and a native array, we're going to have a vector of ints and a list of ints, very much like what we did before. And now what we're going to do is we're going to use the find algorithm. And you can see that find doesn't know, doesn't care whether it's working on a vector or whether it's working on a list or if it's working on a deck or a set or a map and so on. All it cares is that it's got an iterator to the beginning of the range we want to look for an item, and an iterator to one past the end, which is called the last. And as long as it has those two things, it will work transparently, independent of what kind of actual data structure or what kind of data type it's working on. So that's a good example of flexibility. We can, in this case, mix and match things very fluidly without having to rewrite our code. So what this example illustrates is how we can support unanticipated combinations of elements by using something called an adapter. And an adapter is essentially a piece of code that allows two elements or two pieces of software to work together that might not initially have been designed to work together. So, and by the way, this is an example of what the Gang of Four book calls the adapter pattern. So as you can see in this particular example, we have our list and our vector like we did before. And now we're going to move and use a slightly different variant of find. This is called find if, or find underscore if. And there's a whole pile of STL algorithms, all of which end in underscore if. And what the underscore if algorithms do is they take predicates. So rather than trying to find a value, which is what we did here with this version of find, now we're going to be searching on a predicate. And what you're going to see here is we're going to look for the first element in vector v whose value is greater than 5. And this uses a bunch of cool features we'll talk in more detail about probably either later this week or early next week, called binders. That's a type of function adapter. And what we do is we take a binary functor called greater that checks to see whether the first value is greater than the second value. And then we bind it so it can work with a placeholder. That's what this weird underscore 1 parameter is telling us. And so this particular code allows us to be able to make a predicate. We can create a predicate by adapting existing components called negators and binders together to get a predicate that will check whether something is greater than 5. And then down here, we're going to do the same sort of thing, except we're going to apply yet another adapter called a negator in this case. And this is going to go ahead and return the first element that's not greater than 5. So you can see how we can mix and match existing elements in STL in order to be able to do more powerful combinations of features than we can get just by using them in isolation. And don't worry if you're sitting there scratching your chin going, what's a binder, what's a placeholder, what's a negator? We'll cover all that stuff in a lot more detail. Right now, I'm just giving you the kind of bird's eye view of everything in STL. And of course, one of the other reasons why STL has taken the C++ programming world by storm for the past couple decades is because it's very, very, very efficient. And there's several reasons for this efficiency. One reason, of course, is the people who wrote STL were really clever, and they knew a lot about algorithms, and they knew a lot about data structures, and they knew a lot about optimization. So that's one reason. That's kind of the algorithmic reason why it's good. And then there's other reasons, because it supports strong type checking, it all resolves at compile time and link time, and as we'll see, there's no virtual method calls, no virtual functions. So it's really, really, really close to the metal, as it were. And the compilers can do all kinds of inlining to make the overhead just about disappear to nothing, which is yet another great example of zero overhead abstraction in C++ and C++ STL. So here's a couple examples to illustrate this. So one of the things that you can do with STL is you can pass in parameters that will influence the way in which algorithms work. So here you can see we have a vector and a list like we did before. And now we're going to sort both of them. This time we're going to use the proper sort algorithm for a list. And when we call sort on the vector, we say v.begin, v.end. There's an implicit third parameter there, which is called a comparison or comparator function, functor. And this is basically the less parameter. And what less does is it checks to see pairwise combinations of elements that are being sorted to see which one is lower than the other. And because of the way that C++ STL works, that less comparison will be inlined, so all the checks will have no function call overhead whatsoever. So it's as if you wrote the code in line, except you don't write the code in line. You actually write it using these mechanisms called functors, and you can easily replace less with greater in order to get other behaviors, and that can be inlined too. So templates and inlining avoid any function call overhead or any virtual function call overhead. In fact, as we've talked about earlier, C++ STL is really about generic programming, not object-oriented programming. So there's little or no use of virtual methods out of the box with STL. This example also illustrates how you can sort a list. There's a sort method on list that you can just say list.sort or l.sort. And therefore, it doesn't matter the fact that list is not a random access iterator and thus can't use the generic sort algorithm. Instead, it's going to use the one that works with bidirectional iterators, which under the hood is a merge sort variant. And another nice thing that C++ STL does is it also supports strict attention to time complexity of algorithms. So I'm sure you remember from your data structures and algorithms course that you've taken either at Vanderbilt or elsewhere, there's this concept of asymptotic time complexity. And obviously the most efficient algorithms take constant time. It's hard to get that, of course, in many cases, but those are the most efficient. Then we have ones that take linear time in the number of elements. We have other algorithms that take log n time or n log n time, like a lot of the sorting algorithms. And then there are algorithms that have much worse time complexities like n squared or so-called quadratic algorithms. And then there's ones that grow exponentially, and those are horribly difficult to scale even with multiprocessors. And until we have the magic of quantum computing to save us, if that ever happens in our lifetime, we're kind of stuck trying to use typically n log n or linear time algorithms. Well, it turns out that STL is very carefully designed to use linear algorithms or sometimes algorithms with log n behavior and containers log n behavior. So it's really optimized to pick the best breed of the data structures and pick the best of breed of the algorithms in order to get your performance out of the box very efficient, even though you didn't have to write the code yourself. And in fact, that's the beauty of reuse for abstractions like STL, is you can have some of the smartest minds on the planet figure out how to write these components, and then you can reuse them and not have to know or care really how they're implemented under the hood. Okay, so next topic here, and we're still kind of wrapping up our overview of STL. We'll get to some examples here shortly. STL makes very, very heavy use of parameterized types, function templates, and class templates. And we're going to see some examples of both. We've seen a few examples already of function templates in this overview. And then we're also, of course, we've also seen lots of examples of class templates with our discussion of all the stacks we talked about before. So function templates, of course, are C++ functions that can operate on different data types without having to have separate code for each of them. And we'll look at some examples here shortly. Class templates are another variant of parameterized type where we parameterize the types at the class level as opposed to the function level. And so what you're really doing is you're defining a family of classes that are parameterized by type or by value. If a bunch of functions have the same functionality for different data types, like in this case a stack, for example, that becomes a good candidate for a class template. Some things lend themselves to that. Obviously, your famous data structures like stacks and queues and lists and vectors and sets and maps and so on, those are obviously great things to use for class templates. Other things really lend themselves more to function templates, in particular, all the algorithms in STL. And other things lend themselves for sort of a hybrid. So a functor or a function object can typically be a class template with just one, maybe more than one, but usually one method, which is the operator function call method, which is sort of an algorithm. So they kind of fit at the combination or the nexus between containers and algorithms. Okay, so what we're going to do now is we're going to start looking at some examples of generic programming in C++. But before we do that, I'll stop here and see if there's any questions. All right, let's go ahead and queue up things a bit. And let's quit our slideshow. Hopefully this will work. You never know. Oh, there's a question. Can I go over adapters again? So yes, I can go over adapters, but honestly, going over adapters in detail at this point is probably not a best use of time. I will go over them again, though, quickly because you asked the question. But do not worry, we will talk about adapters in much greater detail. So let's take a look at the adapter discussion. Let's see. Where did I talk about adapters? Here it was. So what I'm showing here is that we've got code that we have an algorithm called find if that expects to have a predicate. And one way to do this would be to do something like this. I could say struct. Let's be really specific. Greater. Oh, let's make it a template. Template. Type name T. Struct greater than 5. Okay, that's a pretty darn hard-coded thing to have here, right? And let's go ahead and say bool operator less than, and we'll say T. Say,
Professor, we can't see your screen.
Okay, that's just as well. I will show this to you when I'm done typing it in. Const T ref I and myself return I greater than 5. Okay, so now that I've written this code, I can show you the context or the concept of an adapter, and it will hopefully help with the question. All right, so let's share the screen.